last time we saw a bit about Gaussian wave packets, which I remind you, they refer to free particles in space. In particular, we did it in one dimension, but in fact, the restriction to one dimension is not crucial. You could do very, very similar things in higher dimension. Okay? Now I want to proceed further, and this somehow justifies a little bit the idea that, okay, that if I have a wave packet of this form, psi of x and t equal to an integral over dk, shall we put the square root of 2 pi, why not? Okay, of phi of, okay, e to the I k x minus omega k t, okay, where omega k is such that you have this dispersion, then this describes what it might look like a non-relativistic particle in free space, in one dimension. What about higher dimension? For instance, if I have a particle in 3 dimensions, how would I generalize this? Not difficult. Instead of having this, I put k dotted into x, okay? Instead of using this, I would use the modulus square of k. And obviously the integral has to become a 3-dimensional integral. And here you would have, say, power 3, and this is x. Okay, so this would be the corresponding 3-dimensional expression. And now I want to show you that this object is indeed a solution of this equation, which is a pretty interesting and important equation, which is the time-dependent Schrödinger equation. More properly, the free particle time-dependent Schrödinger equation. So something like this. I will explain to you what it is. The subject, psi of x and t. Is this big enough? Sorry, I forgot to... Joshua, is the writing big enough?
Yes.
Okay, good. So, what is this object here? Is the so-called Laplacian. By the way, mathematicians tend to indicate it like this. Okay, I prefer to indicate it like this because, for a reason. First of all, let me explain to you what it is. So it is the following object. It is the sum of the 3 second derivatives. Okay? I will comment in a second the relationship with the gradient. The gradient, if you remember, is a vector with the 3 first derivatives. This is the sum of the 3 second derivatives. Okay. Now let's consider this particular object. Okay. I'll give it a name. I'll call psi k of x and t. Okay. So it's essentially a single plane wave depending on time with its own omega k. Okay. Single. Now you can verify very simply that it is a solution of this. Okay? In other words, if I put here phi of k, the 2 terms are equal. Let's try. Okay? Left hand side. I have to take the derivative with respect to time of this object. So when I take the derivative with respect to time, what I get is
Negative.
minus I omega k, and then I have the same exponential So let me write it as psi k. Okay? Good. Notice what appears here is plus 1 times h bar omega k. Remember Bohr? Remember Planck, sorry. Okay? Good. So somehow this object here gives you back energies. Let's see what is on the left-hand side, right-hand side. Okay? Let's consider one of these, for instance, this object here. You take the first derivative of this object, so the derivative with respect to, say, x of e to the I k dot x. I don't need to put this because this is just not depending on x, so I leave it out to save some chalk. So this object is the derivative with respect to x of e to the I kx times x plus ky times y plus kz times z, right? Okay. You take a derivative with respect to x, it's this part only that gets affected, and you bring down I kx, right? The same expression, which I rewrite again back in a briefer form, like that, okay? That's general. If you do it for y, you get iky. If you do it for z, you get ikz, okay? So you can, in some sense, also define the gradient operator, the gradient, which is essentially taking the three derivatives, one after the other, okay? Okay, and this gradient operator, when acting on I k dotted into x, gives you back I k e to the I k dotted into x. Is it clear? Okay, the three components are precisely the three components of the wave vector k with an I in front. Okay? Because of that, it is in some sense quite reasonable that if I do the following object, I consider minus I h bar the gradient, okay? When acting on this object, e to the I kx, this will give you back what? I and minus I plus h bar k. Okay? Times the same thing. Now, this is already suggesting that this operator here, it's an operator acting on functions, has these functions here as eigenfunctions, right? You remember what eigenfunctions are in linear algebra. You have a matrix, a vector equal to lambda v, okay? This is called the eigenvector of the matrix A with the eigenvalue lambda. In the same spirit, now I have an operator which plays the role of the A. I have a vector which plays the role of the V, and I have an eigenvalue lambda. Okay? You see the analogy? So this suggests that this operator here has the plane waves as eigenvectors with eigenvalues given by h bar k, if you remember our story about Compton, the Broglie thing, is the momentum of this particle moving with vector k. So the momentum. Okay, for this reason, this operator here will be often indicated by this. Okay, notice it's a vectorial operator, and I put the hat on top to mean it's not just an ordinary vector of three numbers, but is a vectorial operator. So three actions is essentially proportional to the gradient. Okay? In the notes, I would use just boldface for this, and the hat to mean this is the operator, not to be confused with something like this, which is an ordinary vector in some sense. Okay? Good. Now, what about second derivatives? Well, the second derivative is interesting, so I have to take a second derivative now. Second derivative. Okay? So let's take a further derivative here. Okay? Is it clear? Well, when you take a further derivative, you bring down another ikx. Okay? I and I is -1, so the result is minus kx squared e to the I kx. Okay, good. So let's do now the sum of the 3 second derivatives. And you see pretty easily that the Laplacian operator, so the sum of the 3 second derivatives applied to ei to the kx, will give you minus kx squared plus ky squared plus kz squared times the same object. But what is this? This is the modular square of the vector k. Of this object I might call k vector modular square. Nicely. Okay, good. So let's return to our story here. I can erase the algebra. Okay, what is the action of this object here? Minus h bar squared, the Laplacian, over 2m, on this object, which is e to the I k dotted into x, times, and not particularly relevant for the calculation, factor which I pull out. Okay? When I do that, what I get is minus, and the minus is a plus, h bar squared, the modulus of k squared, divided by twice the mass, times the same thing, okay? Which is, in the end, my psi of k. Okay? So you see, indeed, the left-hand side is h bar omega k, and the right-hand side is this. But if you put an h bar here, then that's precisely the same thing. Okay, so the two sides are. In other words, the single plane waves solves this time-dependent Schrödinger equation. Oh, sorry. Too small. I know. But you know how to write Schrödinger. Good. Now I want to show that even this object here, which is a wave packet, so is somehow thinking of any wave function phi of k, not the Gaussian as last time, any you can think of, then you integrate these plane waves, and the resulting thing is a wave packet which could be very complicated. Nevertheless, it solves this problem. How do you prove it? The solution is simple. The Schrödinger equation is linear, as you see. When I say it's linear, I don't mean that there are only linear derivatives. This is a linear derivative, but this is a second order derivative. No, what I mean is linear in the psi, which means I have an operator like the derivative acting on psi. I have another operator acting on psi. I do not have psi squared, psi to the 4, or things like this, okay? So in other words, if two solutions, if I have an equation like this, okay, you can prove and you can realize easily the following fact. Suppose that I have a solution psi 1 of x and t, and then I have a second solution psi 2 of x and t, and then you can form linear combinations like alpha psi 1 of x and t plus beta psi 2 of x and t, okay? Show that if psi 1 and psi 2 satisfy this, then the linear combination also satisfies this. And in fact, linearity is a powerful tool at this point, because not only the sum of two, but the sum of how many you want. In fact, even the integrals do respect this story, and you can do it directly, okay? You try to take the derivative of this here, okay? Obviously, the step you have to make is that you take the derivative inside the integral, okay? Having it acting here, because the derivative with respect to t acts on this guy, okay? So what you, I mean, just to quickly hint to a direct proof of this. If I have this object here, this is equal to the integral in dk over square root of 2 pi cubed. Then I have phi k. The derivative I h bar, the derivative brings you down here h bar omega k. And then the same e to the I k x minus omega kt. Okay? And in a similar spirit, the Laplacian enters inside the integral, acts here, and brings down h bar, k squared, blah, blah, blah. But since these two quantities are the same, the two integrals are the same. Okay? So in some sense, the linearity does the trick, and what we just showed is enough to conclude that these are solutions of the time-dependent Schrödinger equations, the wave packets. Okay. In the geometry, we encounter already two nice actors. One is the momentum. The second is this Laplacian. Let's work on it a little bit more. You see, minus h bar squared, the Laplacian, over 2m. Notice sometimes I put the arrow here. To me, this is somehow the gradient square. Why is the gradient square? If I have the gradient and I dot it into a gradient, for an ordinary vector, what you would do is first component of this, first component of that, plus second, third, okay? And this is what? It would be the derivative with respect to x, derivative with respect to x, plus derivative with respect to y, derivative with respect to y, plus the z, okay? Now you see that acting with two derivatives, one after the other, is nothing but second derivative, okay? So, indeed, this object here, the Laplacian, looks like the gradient dotted with itself, okay? And that's the reason why sometimes I put even an arrow there, although it's not fundamental. I mean, this is a symbol of the Laplacian, which, again, as I told you, the mathematicians like to reverse without the two, okay? I don't find it particularly more transparent. It's presumably less ink because you spare the two, but not particularly fundamental. Okay, good. Now, having said that, you realize that what I do have here is really the momentum operator dotted into the momentum operator divided by 2m, because I have minus I, the gradient. If you just put this expression here and here, you will see that the minus I times minus I gives you a minus, h bar times h bar gives you h bar squared, the gradient dotted into the gradient gives you the Laplacian divided by 2m. So this object is, I might write it like this, p squared over 2m. It's the square of the momentum operator. Square vectorial, obviously, it's components, blah, blah, blah. So nicely, I can also reinterpret this part as the square of the momentum operator, which, as you see, has a pretty transparent classical interpretation. The Hamiltonian of a free particle is kinetic energy, pure kinetic energy, p squared over 2m, being normal relativistic mechanics. Okay? So in some sense, on the right-hand side, I do have a piece which I recognize to be Hamiltonian, kinetic energy, more precisely. Okay? And now I ask you to somehow take an act of faith from you that this is indeed more general than that. Okay? So what Schrödinger actually wrote is that for a non-relativistic particle in any external potential, so not just in free space, what I have is the following equation. Okay? So this is now the Schrödinger equation for a particle in an external potential. Okay? This part of the object is the kinetic energy. This part is the potential energy. And the sum of these two objects, okay, let me write it here, is the Hamiltonian H. Okay? I put the hat to mean it's an operator again. So it's something that acts on wave functions that are in fact on the right. It acts in two ways, the kinetic energy by taking appropriate derivatives with this Laplacian. The potential energy does what? Multiplies. Okay? It's very simple. So this part simply multiplies the function. Warning, these states are no solution if V is different from 0. Okay? So these are wave packet for V equals 0. Okay? Free packets. If you have a particle with a potential, the motion, the dynamics of the wave packet is very complicated. Even if you start from a very simple Gaussian state, it gets distorted a lot. So there's not only the broadening typical of the dispersion, but there is also a lot of other physics related to the fact that the potential acts on the individual components of the wave in a non-trivial way. Is it clear?
Yes.
Huh?
Yes.
Questions so far? Joshua, is it clear? I asked Joshua, obviously I should ask also any other. Puja.
Yes, sir.
Okay. In case it's not, please do not hesitate, okay? All right. Now. Sorry. So, we have encountered already some of the protagonists of these stories that we will tell. Functions and operators, okay? In particular, which operators have we encountered? Well, P, the minus H1, the gradient. Well, there is another operator that is in fact simple. Is X. How does X act on a wave function? It multiplies. So for instance, X psi of a function is equal to X times the function. Okay? Notice the difference. These are intended as an operator, okay? And this is just X back. Obviously, they are almost the same, therefore the distinction is almost irrelevant here because we are using a particular representation of wave functions in real space, okay? We might use a different representation, which is momentum space representation. At that point, the momentum operator would be simpler, the X operator would be more complicated, this in particular, the derivative with respect to momentum. But this is a slightly different story, we will not dwell for the time being with that. Good. What other operators have we encountered? Well, kinetic energy, so P squared over 2m. The potential energy, V of x. The sum of the two, which is the Hamiltonian. So already a handful of operators which you can think of. Okay, good. Now I will teach you a formal way of solving this equation, a formal way, which is the following. To do that, I need some new quantity, which is the exponential of an operator. Suppose that I have some operator, O, okay? And I consider exponential of O. What it is? Well, it is just defined in a very simple way by 1. What is 1? The operator 1.
Identity.
Identity does nothing, multiplies the function by 1. Plus O, Taylor expansion, exactly. Precisely the classical Taylor expansion of the exponential, just substitute the argument with the operator, okay? Plus, well, I could write a compact expression of this type. O to the power n divided by n factorial. O to the power n is n, when n is 0, O to the 0 is the identity by definition, okay? And 0 factorial is 1. So O to the power 1 factorial is this, O to the power 2 factorial, O to the power 3 factorial, and so on. Okay? Very good. Now, it looks like a trivial and identical rewriting of the exponential of functions, but there is a, yep.
This is an operator that we say we are just differentiating. It's an operator, so if I take exponential of an operator, it seems like it doesn't.
It doesn't ring you a bell, doesn't seem to.
Yeah.
Why not? I can take, suppose that this was the momentum, okay?
Yes.
So this would be the first derivative, second derivative, third derivative, and so on. In fact, we will see how important it is, the exponential of something like e to the I times a number, times the momentum, we say in one dimension. It is an operator that translates functions, okay? We'll see this later on. But there is nothing really strange. It is obviously, as you, something which involves all kinds of derivatives. So it's not a simple looking object, but still pretty formally, at least pretty well defined. Okay. In fact, try, okay, as an exercise, in one dimension, try to see what is this. And you will see this is psi of x minus a.
No.
Try. If this is a Taylor expansion, so it's sufficiently irregular, it's minus a or plus a, I forgot. There is a sign that I don't remember by heart. Okay? I always try. Good. The chalk. This I don't like. Let's see if I can get better with this. Maybe. Okay. Good. Now, this looks like standard exponential, but there is one thing that is not standard at all. If I do this, for ordinary exponential, we would just put them together, right? The sum in the argument becomes a product in the ordinary exponential. Here, in general, this is different, okay? The reason why it is different is that the order of operators in quantum mechanics is important. For numbers, the order in the products is not important because the ordinary numbers are commutative when you take the product, right? For quantum mechanical operator, taking O1, O2 is different from O2, O1, okay? And one way to appreciate this is already with a simple example that we already have. Suppose that I do X operator and P operator. This will be useful later on as well. Okay? What this does on a wave function, let's do it in one dimension, is the following. It's X, the P is minus I h bar, the derivative of the wave function, right? Okay, then I multiply by x, and this is minus I h bar x times the derivative of the wave function. Is it clear? Now we do the opposite. I try p after x acting on psi. Okay, p x acting on the wave function multiplies by x. Very good. Now I have to act with p on this, which means minus I h bar, the derivative acting on x psi x. And here you see the difference. Now I have to take the derivative of x as well. So let's do it. So this is minus I h bar. When I take the derivative of this, I get psi of x. Right? But then there is an extra term that is plus x, the derivative of psi of x. Okay. In fact, you recognize that this term is exactly equal to this. But the first term, this one, is not present before. Okay? So in fact, if you take this two object, x, p, minus p, x, okay, acting on a wave function, you see that this term cancels with that, but this remains, and you get I h bar, the wave function. Okay? This is our first example of the fact that two operators do not commute in general, and in particular, an important example of a so-called commutator. Commutator in general for two operators is defined as O1, O2 minus O2, O1. Okay, so it's the difference between the action of the two in reverse order. So this object here is the commutator of x and p. Okay? And the result we just derived is a very important result. Tells you that the commutator of x and p is always equal to IH bar times the identity, obviously. Here, this is a number that multiplies anything. So you could write here in this way, but I will omit consistently the identity whenever it's too trivial. Okay, is it clear? Good. So operators do not commute. Because of that, in general, this is not true. You can realize when you start expanding this, that you will not be able to reconstruct this unless you assume that the order of the factor is irrelevant, which is not in general. Good. But there is one thing that still is true, which is the following. If I take a derivative with respect, say, to a parameter t time of exponential of O multiplied by t, if this was an ordinary exponential, then you would know that the result is O e to the ot, right? And it is, okay? And it is. And in fact, you can put the O wherever you want. Here, for instance, or here. Doesn't matter. The reason is essentially that O commutes with O times T, and with any power of O commutes with O squared or cube or any power, okay? So it really doesn't matter where you put. Let's try to verify. This is a very simple type of algebra, so I'll do it quickly, okay? The derivative with respect to t, so this is the definition of this, identity plus OT plus 1 over 2 factorial O squared t squared plus blah blah blah, right? All terms. Then you take the derivative term by term. The derivative of a constant identity term, nothing, 0. The derivative of O times T is O. The derivative of this, you bring down the 2, and you get 1. So plus O squared times T. Let's do the third, the extra, because you will realize interesting thing from the cube. The 3 divided by the factorial of 3 gives you 2 factorial. So plus 1 over 2 factorial. O cubed stays there, and this becomes T squared. Okay? Excellent. Now you see that there is somehow an imbalance between the powers of the T and the powers of the O. But everywhere you can put out an O. So this is O times T identity plus O times T plus 1 over 2 factorial O squared times T squared plus etc. Okay? And here you see again reconstructed the exponential. Okay? Very, very simple proof, as you see. And by the way, obviously you can put this O in common at the end if you like. Doesn't really matter. Clear? Very good. Now, I use this. So, erase here. And I construct a very useful operator, which is the following. This chalk is bad because it's too soft and leaves strong marks on the board, but unfortunately I cannot find the hard one. So, okay, so I will construct the following operator. U of T is the exponential of minus I, the Hamiltonian, T divided by H bar. Okay? This operator will be very important. It's called the evolution operator. Okay? And it does the following. First of all, let's see what is the derivative of it. Suppose that I calculate I, H bar, the derivative with respect to time of U of T. According to the algebra I just showed to you, what you have to do is to take whatever multiplies T and brings it down. So I have I H bar, which is here, and a further factor minus I A H over H bar, and here I have the same object, so U of T. Is it clear to everybody? Good. I minus I is plus 1, H bar goes, so this is equal to?
It's very,
Huh?
it's Hamiltonian unit.
The Hamiltonian times U. Fantastic. Now I suggest the following thing. Suppose that I gave you some function. Okay, maybe I can erase this. I gave you some function at time 0. I call it psi 0 of x, which is the wave function at time t equals 0. Okay? Then I take u of t and I apply it to psi 0 of x. Okay? This is a function of x and t. Okay? Let me call it psi of x and t. It is a function that at time t equals 0 coincides with that. Why? Because if this is 0, so u of time t equals 0 is the exponential of 0, which is the identity, right? So the evolution operator when the time is 0 is the identity. When the time is different from 0 is very complicated because, as you notice, is all powers, all derivatives, the potential, mixture, a mess, a total mess. Nevertheless, formally, it's well defined. And it does a miracle. It does the following miracle. This object here is a solution of the Schrödinger equation. Okay? How can I prove it? Very, very simple. I take I, h bar, the derivative with respect to time. Sometimes I write the derivative with respect to time as a total derivative, as here. You see this object doesn't depend on x, so I can just allow myself this. In this case, I write as a partial derivative because this object depends on x and t. Okay, so to be more precise, I should, in principle, write as a partial derivative. So let me just calculate this. Okay, according to my prescription, this is still a question mark. I didn't prove it. Let's try. It is r, h bar, the derivative with respect to time of u of t times psi 0 of x. Right? This is my guess. Now, this derivative acts only here, and therefore is just exactly this. And you see that I have even the IH bar in front. So everything is ready, okay? So this result is H times U of T times psi 0 of X. Okay? But this object here, according to my guess, is the psi X of T that I would like to show it is a solution. And indeed it is. Okay? See, IH bar the derivative is equal to H the derivative, which is the Schrödinger equation. Okay? Maybe I should write it in compact form. IH bar, derivative of psi x and t, equal to the Hamiltonian psi of x and t. Okay? This is a compact way of writing this equation. Anyway, compact is very, very general. So even if you don't have a relativistic particle, but you have a Dirac particle, relativistic, still the Schrödinger equation would apply to relativistic particles, but the Hamiltonian that you have to use is the Dirac Hamiltonian, and obviously the wave functions have to be spinorial wave functions. For the nature, more complicated. But formally, in fact, I will anticipate to you a little bit of the thing. When we will work in a more abstract space of vector function, vector states, the Hilbert space, we will see the following. If this is the state of the system, psi of t, then the Schrödinger wave function would look like that. And this could be a complicated thing with many components, spin or 4 components for relativistic particle, whatever, okay? But still the Schrödinger equation would look very, very similar. Okay? And obviously what I just told you applies to those cases as well. So this object here nicely evolves the wave function that you start from time t equals 0 to time t in a non-trivial way. So the shape of this function is totally changed. This shows already the fact that how complex numbers are important in quantum mechanics, because even if you start from a real state, suppose that you have some cosine function, so it's a real function or some combination of cosine. When you apply this operator here, the function that you get on the left-hand side, you see, is inevitably complex. Okay? So you get real and imaginary parts. So there is no quantum mechanics in the real axis only. Okay? You have to invent complex numbers before doing quantum mechanics. Okay. Is it clear so far? Good. So we discovered another important operator, the evolution operator. Notice, it's very important that the Hamiltonian is time independent. If if the Hamiltonian depends on time, and you might ask why, well, it's not very difficult. Suppose that the potential that you put is time dependent. And you might ask, how comes? Well, suppose that you put an electric field or a magnetic field that depends on time. Obviously, the particle will see a potential that should depend on time. So the Hamiltonian can be time dependent. It's in fact an interesting part of the story, but it's more complicated. The evolution operator cannot be written in this form. It's much more complicated. It's called time-ordered exponential. Never mind for that. It's still formally sometimes useful, but certainly not as simple as this. Okay, good. Now let's return to our story. And so far we just played a little bit with this new object. Now we would like to make some contact with a little bit of physics. What is the meaning of this psi of x and t? The interpretation that was given since the beginning by, I think, Max Born, was that if I ask you what is the probability of finding the particle, probability density really, okay, of finding the particle in an infinitesimal small volume close to x at time t, then this object is psi of x and t modulo square. It cannot be psi, you understand, right? Psi, I told you, is a complex thing. This is a probability, so some real positive quantity. It cannot be psi. But, I mean, there are many real and positive things that you can construct out of psi, right? The modulus of psi, for instance, by itself is positive and real. The fourth power of psi is positive and real. Why is the second power so special? Okay, I want to prove you the following fact, that if I pretend that my probability P of x and t respects the following requisites. First of all, is real and positive, as you would certainly want. Second, if I integrate over all space, so this is now the probability of finding the particle somewhere in space, this object here doesn't depend on time. Okay? So this derivative is 0. Now, in particular, since it doesn't depend on time, it's not particularly strange that I can, in fact, require that this object is precisely 1. It's the total normalization. The probability of finding a particle somewhere is just 1. Okay?
Professor, I did not quite understand the B.
The B.
Why is it equal to 0?
The derivative is equal to 0, which means that this quantity is constant in time. Okay, so this is constant in time. I mean, particles are not created or destroyed, probability of finding a particle somewhere is just constant in time. And in particular, you can just fix everything in such a way that the probability is 1. Why do I say fix? Because, I mean, the Schrödinger equation is still linear in psi. So you can multiply the function as you wish by constant, right? So by multiplying the property of the function, I mean, it's very reasonable that I can always normalize the total probability to 1, right? Without really changing anything. But it's important that this is true, otherwise I normalize the function at a certain time, and time goes by and the normalization is lost, right? No, it's not lost, because this is true. Clear? Yep.
Professor. I reckon there is a case where particle is created and destroyed. I mean, in the real world, right? How do you?
This is, first of all, is very common in relativistic theories, most probably field theories, okay, where particles are not concerned. As you know, you can just take an electron and a positron, they can annihilate each other, give rise to other things, photons. Okay, so in non-relativistic theories like the theories of atoms and solids and things, particles are there, okay? I'm not talking about the photons, okay? Particles can make transition and generate photons. Photons are intrinsically non-conserved things. They can be generated, destroyed, absorbed, and do things like this. No, I'm talking about the electrons. The electrons are there. They can escape the system and go somewhere else, but you do not destroy them. By the way, there is a huge energy associated with the mass of the electron. Mega electron volts. Remember, the typical energy scales of atoms is electron volts. So these are like million times bigger. So you do not destroy the electron. It would just make a mess into the system. All right? All right.
I mean, in the case where we meet where the particle is destroyed, where it's not electron, does the probability law change or something?
If it is not,
I mean, we're talking about electron, right? Where the particle is there,
Yeah.
as you said. If we're not talking about electron, does this law change or?
no, but what do you have in mind apart from electron? Obviously protons.
I mean,
So
the
nuclei-
that usually can be created and destroyed.
Which particles?
I don't know. I mean,
That's the
maybe
point.
particle.
They belong to other lecture rooms.
Uh-huh.
In this lecture room for condensed matter, essentially have electrons, nuclei, which just stay together in atoms, molecules, solids. They are not destroyed at all. Okay? That, I mean, there could be chemistry going on. So two atoms approach each other, they form a bond, and they form a molecule which has physical properties which could be very different from the individual atoms. Okay? Some molecules might be toxic, for instance, while the individual atom is not particularly by itself, because they are prone to form ligands with your body or whatever. Okay. So this is a different story. It's chemistry of atoms and molecules, but it's always, nothing is destroyed and everything is considered. I mean, this is the old chemistry type of rule, Dalton's rule, I forgot. Now, the fact that the particle physicists discovered that it is wrong, that you can in fact create particles and destroy particles and create energies with this. So all the story about nuclear energies is in a sense intrinsically related to the fact that you can do things like you are imagining. But that's a different story. It belongs to a different field, and to different energy scales. High energy they are called, high energy scales. We are low energy physicists, so we take care of things that happen in solid and molecules on an energy scale that is much, much lower. Not because of that not interesting, because many things happen at low energies. Superconductivity, superfluidity, magnetism, all these things are low energy phenomena which emerge from the interaction of particles which are not destroyed at all. They just reassemble and do several non-trivial things. Okay? So don't think that because you don't destroy particles, you don't create life is dull. No, there is a lot of physics in the quantum mechanics of non-relativistic systems. Okay, did I answer partially to your question, your curiosity? Okay, now let's prove this thing, and in particular, to prove it, I will show you how important it is that this object is psi of x times psi Okay? Modulus square psi star times psi. Now, we might do it directly. So just, okay, well, first of all, property A is clear, right? This by definition is real. Property B is more difficult. I might just start doing derivatives, integrals, and blah, 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 and verify. But, so this is the only non-trivial property. I prefer to introduce a few more formal tools in such a way that the result comes almost for free. And the extra bonus is that you learn a few more formal tools which are useful in many other contexts. Okay? Do you want to stop for a couple of minutes? Just to... I want to stop. Okay. Okay, we start again. And the formal tools that I want to introduce is a scalar product. We have functions, okay? If we had ordinary vectors, you would know how to introduce the standard Euclidean length of a vector, the standard scalar product of the two lengths times the cosine of the angle, and things like this. If you have done some linear algebra, you know how this thing generalized to any vector space. Now I want to consider my space of functions, psi of x, as somehow a linear space. So I can add two functions, I can multiply a function by a complex number. So this is a linear space of functions. And in this linear space, it makes sense to try to introduce a length and a scalar product. Let's see how to do it. Suppose that I have two functions, psi1 and psi2. I want to introduce the scalar product of psi1 and psi2, okay? And I denote it by this object, so not, if these were ordinary vectors, I would write this. I have a different notation, is this. By the way, mathematicians might use round parentheses, never mind, okay? I use this angle parenthesis because Dirac was using this essentially. And the definition is the following. You take the integral, these are, I want a number, this must be a number, okay? Complex number in general, because the two functions are complex, so I want a complex number. But out of two functions, so I take an integral, and I take an integral of the star of the function on the left times the function on the right. Okay? This is my definition of scalar product. Let's see if it makes sense. For instance, you remember that if I have a scalar product of an ordinary vector, v dot v is the length square, the Euclidean length square, right? Now, what would be the analog of this? Psi1 dotted into psi1 is the integral of the x of psi1 star psi1, right? So the modulus square of psi1. Okay? Nicely is the integral of the modulus square of the function of row space. So it's a positive quantity that tells you how big is the function, right? Function is very big, big modulus square, you integrate, and this is big. So it tells you the length, so to speak, of this function. It's not the only length that you can introduce, it is called the L2 length, because of this 2. You can introduce other lengths, mathematicians have done lots of things. This is in fact, in particular, also denoted by psi1 modulus square. This is a norm. Okay, this is called a norm. Norm. And it is called in particular the L2 norm. Okay, good. Immediately you realize that there are functions whose total norm is finite, which are called normalizable, and functions which cannot be normalized. Let's revise our function we know. The plane wave, for instance. Nice functions, right? They allow you to write Fourier transforms and things. Are they normalizable or not? No. The modulus square of e to the ix is equal to 1. So this integral here is the integral of 1 over all infinite space is infinite. Okay? So the norm of this object is infinite. It's not normalizable. All right. So in some sense, this already restricts functions in the states in different classes. And I will define a particular class of those functions. It's called the Hilbert space. It's the class of function psi of x such that the norm of psi of x is less than infinity. Okay? So they are normalizable. This is the Hilbert space of the system. Functions, okay, complex, whose total norm, so total integral, can be calculated and is finite. Strictly speaking, the pure plane waves do not belong to the Hilbert space. Nevertheless, they are so extremely useful that we keep using them as a formal tool, at least, to calculate Fourier transforms of things. Okay, good. In this space of functions that are normalized, you define this scalar product. So this is known as scalar product between two functions. Okay. Good. What else can I do? Well, I can apply an operator. Where should I write? I raise this, okay, for a while, and I will rewrite it when needed. Okay? So suppose that I take an operator, I apply to a function, okay? And then I take a scalar product of this object with psi 1. I can certainly do that, okay? So concretely means integral of psi 1 star times the operator applied to psi 2 at position x. So I can do that. Now, there are cases where this thing is equal to applying the operator on the left and then taking the operator, the scalar product of psi 2. Not for all of them, but if this is true, you say that O is Hermitian. Okay? So Hermitian means that we can go past the border without passport. Okay? Very, very nice. Freedom. Good. Let's see if we can write down one operator that is certainly Hermitian. Pick of x multiplied by x, which is a real quantity. Okay? So passing the border means the star, but the star to a positive function, real function doesn't, sorry, not positive, to a real function doesn't make no difference, right? So certainly, if I try to write psi 1, say x, think of one dimension, so no vectors, okay? Psi 2 is equal to x of psi 1, psi 2. Are you convinced about this? Should I write the two integrals? Are the same, right? Because the star of the x is just x. Good. So there are certain operators that do allow you to go across the border. What about p? Let's try with p. You might think, no, p, poor guy, has an I, right? Remember p, the momentum operator, again, let's do it in one dimension. There's an I there, so as it goes to the left, you get plus, not minus I. Too bad. No. Just because of this I, You can go back and forth. Because remember that when you bring the derivative on two sides of the thing, integration by parts tells you that there is a minus sign. Okay? So that rule of calculus that tells you that when you do integration by parts, the derivatives exchanged has a minus sign would be very bad if the momentum was just this. It would not be emission. But because of this I, it is emission. Okay? So I'll now prove for you that P is in the dimension. Let's do it. So I have a function P minus I h bar, the derivative of another function. Okay? Like this. What it is? We erase this. It is equal to the integral in x, one dimension, to simplify things, psi 1 star. Okay, then I have minus I h bar, the derivative with respect to x of psi 2 of x. Is it clear? That's the integral that I have there. Okay, now this minus I h bar can go here, and I have simply this integral. Let me just write it like this. Okay, now you recognize the typical thing that would call for an integration by parts, right? You can move this object here to this term, except for a boundary term. Remember, when you do integration by parts, you take the primitive. Okay, let's do it together. Okay, what you would say is, okay, the integral of this is psi 2, so I have psi 1 star of x, psi 2 of x, and I should calculate it between plus infinity and minus infinity, and then I have opposite sign, the integral of the derivative now acting there, so the derivative acting of psi 1 star of x times psi 2 of x. That's integration by parts that I have used, right? Okay, let's look at the boundary term. Is the functions at plus infinity and the functions at minus infinity. But these are normalizable functions. They belong to the Hilbert space, right? And therefore, they should go to 0 at plus infinity, otherwise the integral could not be. Okay? So because of this term here is 0. Alright? Good. Now you might say, hey, but this is not equal to, well, what should be equal is, let's see, to P psi 1 psi 2. What is P psi 1 psi 2? Let's write it. Integral of minus I h bar, the derivative of psi 1 of x, star. Okay, on the left I have a star, times psi 2 of x. Let's see if it is equal or not. It is equal, right? Because this is a plus. So this is equal to plus I h bar, the integral of the derivative with respect to x of psi 1 star times psi 2. Is it clear? And this is precisely the same, because when you take the derivative, you get the derivative. When you take the star, you take the derivative of the star, and the star of this gives you plus I. Okay? So the two things are identical thanks to the I. Without I, it wouldn't be emission. Okay? Fantastic. Now, let's see other proposals for emission operators. If I have an emission operator and I square it, do you think it's emission or not? So the question is, suppose that O is emission. Would O square be also emission? So in other words, would this be true? Question mark? No, why?
Because it's real.
Let's see. Okay. O is emission, right? Well, this is equal to O times O. Okay? So because it is emission, I can bring this to the left-hand side, right? So this is equal to O psi 1, O psi 2. But O is emission, so I can bring also this to across the border. No possible. Okay, so this is equal to O squared psi 1 psi 2. Okay? So the square of an emission operator is emission. The cube is emission. Any power is emission. Alright? In fact, any functions that can be Taylor expanded function with an argument equal to the emission operator is emission. For instance, the exponential of an emission operator is emission. Notice the unit, the evolution operator is not the exponential of an emission operator because there is an I there. We'll see, it's interesting. They are called unitary operators. Different, okay? Later on. Good. So suppose that the powers are fine. What about the sum of two emission operators? If I have O1 emission, O2 emission, is O1 plus O2 emission? Yes. Good job. Everything here is linear, okay? So for instance, if I have, just to remind you, O1 plus O2 acting on psi 2, okay? This means, look at the definition, this means psi 1 O1 applied to psi 2 plus psi 1 O2 psi 2. Because these are linear operator and the scalar product is linear on the right part. Essentially also linear on the left, but there is this star, so you call it anti-linear. Because there is a slightly different behavior with respect to the complex things, okay? So on the right, even if you put some i's, it's still linear. On the left, you get some minus sign. So, but I mean, the linearity is basically there both on both sides. Okay. This suggests that if I have maybe there is two conflict between 1 and 2 and 1 and 2. Let's call it A and B. Okay. So it is more clear. For each of them, I can bring it there. And then I can collect again the two things because of linearity. And the result is that the sum of two emission operators is emission, which means that based on X and P, many operators are emission. Any potential, as long as you can Taylor expand, is emission. P squared, kinetic energy, is emission. The sum of P squared plus the potential, remember the Hamiltonian is the sum of P squared, which is emission, plus V of X, which is emission. Okay, so the Hamiltonian itself is emission. Okay, let's yeah.
Can you repeat what you say about anti-linear and linear in the equation? I think you said about something about anti-linear.
Yes, the point is the following. The point is the following. If I have psi 1 alpha psi 2, so I multiply by a constant this is equal to alpha psi 1 psi 2. This is now a constant, complex constant, okay? But if I write this alpha psi 1 psi 2, this is not equal to alpha times the thing, that is alpha star. Okay? This is not a standard linearity, it is the linearity with a star. And sometimes this makes a little bit of difference in certain things. you call it anti-linear, but it's not particularly relevant at this time. It's important in the theory of time universal symmetry, and we will see, no, we will probably not see it, but if chances, I mean, if you will occur more later about this, I will reopen the discussion, but it's not particularly relevant. I don't want you to confuse you. Okay, now, I introduced all this machinery because I wanted to do that. Okay, so far this was very, very formal tricks. Let's see why. After learning those things, you can solve the problem in a second. Let's see. Yeah. Yes.
V of x is dimension because it's real.
What?
V of x is dimension.
Yes, it is a real. Of course, it is a real potential. Okay. Now let's discuss. I told you that the complex things are dangerous. Okay. So if I take, say, an operator like x, and I multiply by 3i, this operator is no longer Hermitian. Okay? For a very simple reason, that when you bring to the left, the I lets you pay the price, the minus sign. Okay? So in some sense you get the star there. Right? And so because of that, yes, real potentials, which are the physical potential, although people introduce sometimes complex potential to allow for dissipation of things that decay and so on and so forth. But this is a more advanced topic, and I would not touch it. Okay, so for us, the potentials are always physical, real potentials. Later on, we will encounter the I playing some roles, but for the time being, I will not. I will not use it. Okay. Now, let's look at this expression. Okay, so I have the derivative with respect to time of the integral with respect to x of p, which is psi star x and t times psi of x and t, right? So first of all, well, I can certainly enter the derivative. We are physicists, okay? So we're not worried about the fact that the derivative and the integral, there could be the dangerous cases where you cannot do that. No, we can always do that. But there are two places where the derivative acts. One is that and one is that. Okay, for this, it's simple. I know that I h bar, the derivative with respect to time of psi of x and t, is equal to the Hamiltonian acting on psi of x and t. Right? But what about when you act here? I do have the derivative with respect to time of psi star. Well, okay, let's take the star of this. So minus I h bar, the derivative with respect to time of psi star of x and t is equal to h psi of x and t star. Right?
Yeah.
Good. Okay, so let's do the algebra. So this is equal to the integral over dx of the derivative with respect to time of psi star of x and t times psi of x and t. Okay, plus psi of x and t plus times the derivative of psi of x and t. Okay, good. What is this? Well, we do it like this. I put 1 over h bar h there. And what is this. Okay, it's so here is minus IH bar. Okay? So there is just a minus sign and a plus. Okay, so I do it. And this is equal to 1 over minus IH bar. The H psi to the left. Okay, so the integral over x of H psi. Let me just spare some variables to the left times psi, okay, and then I have this term is plus 1 over IH bar, the integral. Now I have the psi star on the left, and on the right I have H psi. Okay? Do you recognize what these objects are? Let's look at this object. What is it? Scalar products. That's the suggestion. Okay, so this object is psi, sorry, because it gets the star automatically, applied to H psi. What is this? H psi applied to psi. Ah, they're related, right? Because you know that H is a relation. So these two objects are actually the same thing. H can cross the border. Oh, fantastic. So there's a plus and there is a minus. Okay? So the result is 0. Okay? So very nicely, by just having a few more formal tools, which are useful anyway, the proof that this object is conserved is triggered. Okay? Due to the fact that the Schrödinger equation is governed by an Hamiltonian, which is a mission, then the modulo square is automatically guaranteed to be conserved if you integrate over all space. Okay? Which is property B. So it doesn't depend on time. We prove that this object is 0. This 0 here is precisely the 0 we wanted. Okay? Now, because of this conservation in time, if you have at a given time a perfectly changed away function in such a way that the total integral, this total probability is 1, it stays 1 forever. So property C, which I erased for us. Is it clear? Good. I think that this is almost time to stop.
Professor,
Yeah.
can you repeat the relation between B and C?
B and
C.
T or C?
C.
C. C is telling me the following thing. C was this, that I can take the integral over x of P of x in T equal to 1. The argument is the following. Suppose that the choice I made of my psi was not 1, but this was 4. Okay? Let's be more general. Suppose that this was the square alpha squared. Okay? And alpha is any number you want. Then my proposal is the following. Take a new function, psi tilde of x and t, which is equal to 1 over modulus of alpha times the function psi of x and t. Okay? First of all, with this new function, the total integral over space of psi tilde x and t star, or if you want modulus square, is equal to 1, obviously, because if the total integral of the psi modulus square is alpha square, you divide by alpha and alpha, and the result is 1. Okay? You might ask, yes, but you changed the function. Yes, but I changed the function by some coefficient in front. And if this is a solution of the Schrödinger equation, this is still a solution of the Schrödinger equation. So another constant in front is not important in the wave function. I can always rescale it. Okay? Thanks to the fact that this is somehow independent of time, if I normalize it correctly for time t, then you're sure it's normalized correctly at all times. Is it clear? So that's the argument behind. Good. One last thing because before we finish. The notation that I use here is such that, and you have seen it, for instance, there, okay? If I have an operator acting on, say, the function on the right-hand side, okay, I write it like this, okay? There is a slightly different notation due to Dirac, which is the following: psi 1, operator, psi 2. So now the operator stays in the middle, in between those two bars, and there's the state on the right and the state on the left. Okay, by the way, this is called the ket, and this is usually called the bra for a very, the reason is historical, essentially. In this way, the operator is in bracket, okay, so it's a kind of mot d'esprit. Is it, but there is a lot of history of this. Dirac introduced it, and therefore you will often see things like this. Will be states in between the space called also kets, abstract, so not only wave functions. The two things are absolutely the same thing. Okay, later on we will discuss a little bit more about the meaning of the bra and sometimes the usefulness of the Dirac notation, but sometimes it's dangerous, okay, especially when we have anti-linear things. So for time reversal, I want to always to think possibly in both ways. So where is this operator acting? On the right, on the left, what is he doing? Okay, so be ready to shift your mental attitude in case you feel confused. Okay? All right. I think I should end here. Or maybe.
Can I?
Yeah. Yeah. Please.
What's the connection with that equation equals to 0, and then the connection with C or maybe?
What I prove is that the derivative of this object is equal to 0, which is B. Okay? Because that object, this is P. According to Born rule.
Born rule.
Which is this. The probability is the modulo square of psi. If you remember, the energy of an electric field, an electromagnetic field, is the modulo square of E plus modulo square of B. It's not the field itself, not the modulus of the field, it's the modulus. So in some sense, by analogy, the probability, physical quantity, is not psi, not the modulus of psi, is modulo square of psi. And the overall justification of this is it makes sense. Probability is conserved in this way. If you put the modulus to the power of 4, it wouldn't be conserved. Okay? But this is already something that makes modulus to the power of 4 a fishy thing, right? All right? So you understand that it shouldn't be right. But this is Born rule, Max Born, not Born, not Niels Bohr, Max Born.
Yeah, the Born interpretation.
Huh?
The Born interpretation on quantum.
Yes. But this opens chapters which I wouldn't like to open about the interpretation and philosophical aspects of the story, although some of these aspects are kind of, with time, emerge as important things and not purely philosophical distinctions. But yeah. Okay, I think I should end the discussion here. Next time we will proceed by just explaining a few other formal tools, and finally we prove Heisenberg uncertainty principle again in more general terms. We'll discuss the continuity equation, the concept of current operator, and so on and so forth. Okay? So this will come next week. Okay. If there are no questions, I can end.
I have one more.
Yeah, please.
So one, you said that if we multiply the operator x by I, we cannot get it Hermitian again.
Yeah.
But what if we multiply the operator x in momentum space by I? Like, will it be Hermitian again?
I don't know if I understood correctly, but for instance, this operator, derivative with respect to p, suppose that I have a function of p, but this requires that I think in terms of momentum space representation, which I haven't explained to you. It's essentially a Fourier transform of the wave function, but I didn't explain it to you, so it's a bit... so if I apply this object to phi, and I multiply by I, that's totally equivalent to x. Okay, so the x in momentum space is this to the next part. But I don't know if you ask this, so I'm answering.
I'm asking whether it is. You said it's not conserved or not Hermitian. I forgot the term, but.
Hermitian.
Yeah, but in momentum space, what will happen?
Something, if it is not Hermitian, it's not Hermitian in any representation. This is momentum in real space is called representation. Okay? Any representation, it's not Hermitian. This is not because you're doing momentum in real space. It's not Hermitian. There are examples of interesting operators. Let's consider this operator. We will see that by defining things like this, we will be able to solve algebraically the harmonic oscillations. This is an interesting operator. It's called A dagger, or A. Okay? These are not Hermitian, because X is Hermitian, P is Hermitian, but there is this I, and this combination is not Hermitian. So in some sense, the dagger, okay? Next time I will discuss about the Hermitian conjugate, okay? So far I have an operator like H. The Hermitian conjugate of H is equal to H. Next time I will discuss what is the concept of Hermitian conjugate in full generality. So if I have an operator that is not Hermitian, how do I take its Hermitian conjugate? Okay? Next time. The answer is that if I take this, I have X minus IP. Because both of these are Hermitian, but this object brings me minus. Okay? So next time we will have things like this expressed better. Good? Okay, now stop.